Hello everyone, my name is Xiaoyi Lu, a research scientist from the Ohio State University. Here I'm going to present a tutorial about how to measure and understand the MPI-level communication performance on Chameleon Cloud, and to show some demos of using MPI-2 based MPI bare metal appliance on Chameleon Cloud. So this tutorial was prepared by myself and my colleagues. They are Jie Zhang, Shashank Gugani, and Dr. D.K. Panda from the Ohio State University. So this is the outline of the presentation. First, I'll give an overview of MPI-level communication and show how to deploy MPI bare metal Infiniband clusters on Chameleon, and give some examples of running OMB with MPI-2. OMB is OSU MPI micro benchmark, and we also give some additional exercises. So first, let's take a look the overview of MPI-level communication. MPI is short for message passing interface. It provides different kind of operations. So for example, you can do point-to-point two-sided communication like MPI send and receive. You can also do point-to-point one-sided communication, like you can use MPI put and MPI get to put and get data from and to remote process. You can also do different kind of collective communications. For example, MPI bcast to broadcast the data to word processes, and you can also do MPI auto. So it means you can word process exchange information to and from other word processes. MPI also gives some other operations like MPI init and finalize, so you can initialize and finalize the MPI environment. Some other concepts like communicator and rank are also important for you to understand MPI programs. MPI is an industry standard model for parallel programming. The latest standard version is MPI 3.1. So you can get more information through MPI standard this link to get the all more details about MPI. And in API forum, this link here, you can also get to know that more recent discussions about some advanced topics about MPI. So there are many different implementations of MPI exist in the community, both for commercial and public domain. So in this tutorial, we'll use MPI-2, which is developed by OSU group. So this link provides more detail about the MPI-2 project. Things we are going to understand MPI-level communication and measure the performance of it. So we have to use some benchmarks to do the experiments. So in OSU group, we have developed OSU MPI micro benchmark called OMB suite. This benchmark suite covered a lot of different perspectives of MPI performance measurement. So OMB is a comprehensive suite of benchmarks to compare performance of different MPI libraries on various networks and systems. It can be used to validate low-level functionalities. It also provides insights to understanding the underlying design of MPI libraries. This OMB suite started with basic send-receive micro-benchmarks for latency bandwidth and bidirectional bandwidth. Later on, we have extended this benchmark suite to cover more functions like MPI one-sided operations, MPI collective operations, and also GPU-aware data movement. And because recently MPI plus PCAS hybrid program model is becoming very hot, so in our OMB benchmark, we have included some OpenSHMEM point-to-point collective benchmarks, and we also support UPC parallel programming language benchmarks for PCAS program model. OMB has become an industry standard. It has been extensively used for design and development of MPI libraries. We can use OMB to do the performance comparison of MPI libraries and in all different kind of large-scale systems. It is available through this link. Okay, it's also available in an integrated manner with MPI-2 stack, which means if you download our MPI-2 library, after you install it, you will see that OMB is there. Okay, so next, things we are going to run these benchmarks. So we have to have an environment to run it. So the next thing is to deploy MPI bare metal InfiniBand clusters on Chameleon. For how to deploy MPI bare metal InfiniBand cluster on Chameleon Cloud, we have a separate video called MPI How to Run MPI Programs on Chameleon Cloud. There we have all detailed steps to deploy MPI bare metal InfiniBand clusters through our MPI-2 complex appliance. So if you want to try, you can go to Chameleon Cloud. This is the link. And if you want to get more information about the complex appliance, our MPI bare metal cluster complex appliance on Chameleon Cloud, you can go to this link, get more information about this appliance. Okay, let's assume that you already deployed some nodes in the Chameleon Cloud. Okay, so now let's show some examples of running OMB with MPI-2. So in this tutorial, we will cover 3 different categories of this benchmark. So the first one is MPI two-sided point-to-point operations. We will use MPI latency benchmark and MPI bandwidth benchmark. We will run these benchmarks in both Intra-Node and Intra-Node scenarios. And the second category is MPI one-sided point-to-point communication. We'll use MPI put latency benchmark to do this. And for the MPI collectives, we'll run MPI broadcast and the MPI auto benchmark over 4 nodes. And each node will run 16 processes, which means that in total we have 64 processes running. Okay, first let's see how to run MPI point-to-point two-sided latency benchmark for the Intra-Node case. So this is the command we use to run this benchmark. First of all, you have the MPI run RSH is a tool that can help users launch the benchmark in parallel. Okay, so there's a parameter called -np, means number of processes you want to launch. Here give 2 means we have 2 processes get launched to run this benchmark. And then this host names, MPI instance 0 and then MPI instance 1 means these 2 processes will be launched on these 2 nodes. Okay, each of these 2 nodes will have 1 process. So that's why we call this Intra-Node case, because these 2 different nodes. This is the output of this benchmark. This latency benchmark are carried out in a ping-pong fashion. The sender sends a message with a certain data size to the receiver and waits for a reply from the receiver. And the receiver receives the message from the sender and sends back a reply with the same data size. Many iterations of these ping-pong tests are carried out, and average one-way latency numbers are reported. So this is the average one-way latency number. Okay, as we can see that if you see these numbers, it looks very good. For example, for 1, 2, 4, even go up to 64 bytes, we are almost only take around 1 microsecond. This is very fast communication. So if, for why these numbers look so good, the main reason is because we are using MPI-2 over Infiniband networking technology. So Infiniband is a very popular high-performance network which has been used widely on top 500 supercomputers. Infiniband provides high-performance data transfer. It can do inter-process communication and I/O in a very fast manner. It gives your application very low latency. For example, like I said, it's only around 1 microsecond, and it also gives high performance, high bandwidth. For example, for the latest Infiniband EDR card, you can achieve around 100 Gbps bandwidth, and it also only needs a very low CPU utilization during the communication. Is around 5 to 10% of the CPU utilization. Infiniband also support multiple kinds of operations. You can do traditional send-receive based communication. You can also do RDMA based read and write. Infiniband also provide atomic operations. This is very unique. These atomic operations have been used in many fields. For example, distributed logs, semaphores, and collective communication operations. Okay, the MPI-2 MPI library developed by OSU Group provides a high-performance open-source implementation of MPI standard for Infiniband network. MPI-2 also support other networks like Omnipass, iWarp, Rocky. So this is the link for MPI-2 project. If you want to get more information, please go there and take a look. Okay, we show the OSU latency Intra-Node numbers. Now let's take a look Intra-Node case. So this is the command line to launch the same OSU latency benchmark in the same node. So similarly, we run two processes, but for the host name, we just put the same host name here. So which means we run these two processes in the same node, like MPI instance 0. Okay. So if you see these numbers, we found that intra-node latency numbers are much smaller than inter-node latency numbers. For example, earlier we see that 1 byte is around 1 microsecond, right? Here is only around 0.2 microsecond. This number looks even better. The main reason is because of that in our MPI-2 library, as long as we see that the two MPI processes in the same node, we will automatically make sure that the communication transfer between these two processes will go through either shared memory channel or cross memory attached CMA channel. So for small message size, the communication will go through shared memory channel. For large message sizes, the communication will go through CMA channel. The main reason is because for shared memory channel, you need to do 2 copies. For the CMA channel, you just have to do 1 copy through the help of the kernel, Linux kernel. So which means the CMA channel can provide good performance for large message size because you can avoid 1 copy. Okay. Now let's take a look at the MPI point-to-point two-sided bandwidth test for inter-node case. So similarly, this is the command of how to launch the OSU bandwidth test in the in 2 nodes, MPI instance 0 and MPI instance 1. Okay, this is the output of the this test. The bandwidth tests were carried out by having the sender sending out a fixed number equal to window size of back-to-back messages to the receiver and then waiting for a reply from the receiver. The receiver sends the reply only after receiving all these messages. This process is repeated for several iterations, and the bandwidth is calculated by the elapsed time and the number of bytes sent by the sender. Okay, so this is the output. As we can see that we are able to achieve near to the hardware peak bandwidth of Infiniband FDR card. In Chameleon, currently we are using Infiniband FDR card. The theoretical peak bandwidth is around 56 Gbps, so it's almost close to that. So that slide is for the inter-node case. Now this slide is for the MPI point-to-point two-sided bandwidth test for the inter-node case. Similarly, as long as you put the same host name here, so these two processes will be launched in the same node. So as we can see that the inter-node bandwidth numbers are much higher than inter-node bandwidth numbers. The main reason is like I said earlier, for the inter-node case, MPI-2 MPI library will automatically make sure the communication goes through either shared memory channel or CMA channel. So here, like I said earlier, we see around 6,000 megabytes per second. Now here is around 12k megabyte per second. Okay. By the way, as long as you're using our MPI-2 appliance to deploy your cluster, or the MPI-2 MPI library as well as the OMB benchmark suite will be automatically installed for you. You don't have to do anything. So this is the path of the default installation. Okay, OPT MPI-2, and you can find the OMB here. Okay, so those experiments for MPI point-to-point two-sided operation communication. Now let's take a look at MPI point-to-point one-sided communication. Here we use OSU put latency benchmark to do the experiments. Similarly, this is the command of how to launch this benchmark, and then this is the output of this benchmark. So in this benchmark, we have include different window initialization operations because in MPI 3 RMA standard, you have different ways to do the window creation and the different ways to do synchronization operation. Okay, so in this benchmark, we support all these different in window initialization and synchronization operation. For example, win create, win allocate, win create dynamic, and for synchronization, we can have win lock, unlock, flash, flash local, flash lock or unlock, win post, start, complete, wait, and win fence. Okay, so you can select different combination of this to do the experiments, and then the latency reported here includes the data communication and the synchronization time. Okay, the window creation time is not included here. And if you run this benchmark, we actually also print the window creation operation being select and the synchronization operation being select. So for this default case is MPI win allocate and MPI win flush. And okay, that's example for MPI one-sided point-to-point one-sided operation. Now let's take a look at the examples of MPI collectives. Here first, let's run the broadcast example. So this is the command of how to run OSU bcast benchmark. So like I said earlier, we will run 64 processes over 4 nodes. And the things earlier we used host names put here, but because if you put 64 host names, the command will be very long. Another way to provide the host names is through a host file. So you can create a host file like hosts-64. You can write the host name line by line in this file, and then use this parameter to let the MPI run RSH tool nodes with the host file. Okay, so through this you're able to launch 64 processes across different nodes. Okay, this is the output of bcast. The OSU bcast benchmark broadcasts a message from the process with rank root to all other processes of the communicator. This benchmark measures the min, max, and average latency of the MPI bcast collective operation across n processes for various message lengths over a large number of iterations. Average latency will be reported by default. This average latency. And similarly, you can use a similar command to do the experiments with MPI all-to-all collective benchmark called OSU all-to-all. Okay, for in this benchmark, all processes will send data to all the processes, so that's why it's called all-to-all. The benchmark will measure the min, max, and the average latency of the MPI all-to-all collective operation across n processes for different message lengths over a large number of iterations. Similarly, average latency is reported by default. Okay, this we just give some examples of how to run OMB with MRP2 over Chameleon Cloud. You can also do additional exercises. Here we list some of them. For example, for MPI point-to-point benchmarks, two-sided case, you can run OSU MPI bidirectional bandwidth test. The benchmark name is OSU underscore by bandwidth. And then you can also do OSU MPI multiple bandwidth or message rate test. The benchmark name is OSU underscore MBW underscore MR. And then for MPI point-to-point one-sided benchmark, you can also run OSU MPI get latency test. The benchmark name is OSU underscore get underscore latency. In our earlier slides, we showed the put latency benchmark. You can do similar experiments with MPI get latency benchmark. For collective benchmarks, we have provide another examples you can run here. One is OSU MPI or gather latency test. The benchmark name is OSU underscore or gather, and OSU MPI scatter latency test. The benchmark name is OSU underscore scatter. So if you use our appliance, deploy the bare metal cluster in Chameleon Cloud, you can automatically get all these benchmarks installed in your nodes. You can also try to run with different number of processes for these benchmarks. We have provided some sample numbers in our MRP2 project website, like this link shows. You can also see whether your numbers look similar to our reported sample numbers. And for more information about MLP2 library, you can go to this link about about the user guide of MLP2 library. You can get more information and about the advanced features of MLP2. Okay. This is the web pointers about our Lao lab and as well as MLP2 project. These are our emails. If you have any questions, please feel free to contact us. Thank you.